So let's talk about projected coordinate systems. The Cartesian coordinate system is planar, two-dimensional grid coordinate system based on two axes, the x-axis and the y-axis. Once one transforms the globe into a plane, a Cartesian coordinate system defines locations on the map. This type of spatial reference system is commonly called a projected coordinate system, or PCS. For large-scale maps, projected coordinate systems measure distance in areas with a high degree of precision and accuracy. The x-axis represents positions in the east and west directions, while the y-axis represents positions in the north-south directions. When converting latitude and longitude into Cartesian coordinates, the grid is divided into four quadrants, using the equator and the prime meridian as the x and y axes. You then assign negative numbers to west and south latitude and longitude coordinates using decimal degrees. However, many projected coordinate systems do not use latitude and longitude and take measures to avoid negative numbers. All projected coordinate systems originate from a specific geographic coordinate system and datum. The geodetic datum used as a basis for any projected coordinate system influences the position of the coordinates. It can be really confusing. It's important to be aware of which datum on which the projected coordinate system is based, making sure it is the optimal datum for the region of interest. So we'll talk about a couple of projected coordinate systems today, just to give you guys an example of two really common ones that we use, especially in this class, because we're doing a lot of work with data in California and then more specifically in Humboldt County. So first we have the Universal Transverse Mercator, or UTM system. The UTM system is an international grid coordinate system based on the transverse Mercator projection. It consists of a series of 60 north-south strips of Earth called gores. Created by rotating the transverse Mercator projection so that it centers on each gore, each is 6 degrees longitude across. The gores are cut in half at the equator, creating a series of 120 sections called UTM zones. The UTM system extends 84 degrees latitude north and 80 degrees south. Each UTM zone includes a number and a letter for identification. Zone 1 starts at 180 degrees west. The numbers increase moving from west to east. The last zone ends with the number 60 and 180 degrees east, centered over the eastern end of New Zealand. The letter N represents the northern hemisphere and the letter S for the southern hemisphere, and they follow the zone number. Each UTM zone has a Cartesian grid coordinates utterly independent from the others. The UTM system ensures that all coordinates in the system are positive numbers using a system of eastings and northings. You can think of it as forcing all coordinates into the first zone of the Cartesian coordinate system. The UTM system accomplishes this by designating an arbitrary point of origin for the x-axis and y-axis to the southwest of each zone. An easting is the x-axis coordinate measured in meters east of the origin. The central meridian, a line of tangency for the transverse Mercator projection of each zone, has a false easting of 500,000 meters. A false easting, a false easting is just the value given to grid coordinate systems on the x-axis so that all x-coordinates in the system are positive numbers. Eastings can be pretty confusing. The question of where the origin is commonly comes up, but the answer always is the same. It does not matter. The origin of every zone in the northern hemisphere is west of the zone and at the equator. Every zone centers on 500,000 meters east. The coordinates everywhere else in the zone are relative to that origin. The y-axis has a value called a northing. In the northern hemisphere, this represents the number of meters north of the equator, which has a value of 0 meters north. In the southern hemisphere, the UTM system assigns the equator of a false northing of 10 million meters, which corresponds to 80 degrees south. Like the false easting, a false northing for the southern hemisphere ensures that all the coordinates in the system are positive numbers. Coordinates in the UTM system are written using the notation x-axis meters and then y-axis meters, followed by a zone. So this would be UTM zone 10 and the hemisphere that it's in north. And then of course, your X meters are in the east and your Y meters are in the north. The UTM system is highly accurate and due to its accuracy, global extent, and consistent structure, the UTM is the most useful spatial reference system in the world. Okay, so we also have the state plane coordinate system. Many countries establish local projected coordinate systems for highly accurate measurements over a small region. The United States uses a projected coordinate system called the State Plane Coordinate System, or SPS. Like UTM, the State Plane Coordinate System is also a grid coordinate system based on zones. It also uses eastings and northings so that all coordinate systems are positive numbers, but boundaries for these zones follow political boundaries, and in California, they follow the certain county boundaries. Unfortunately, the SPS does not have a consistent structure nationwide, so it is only useful for localized regions within a specific state and does not work well across state lines. The most recent version, the State Plane Coordinate System of 1983, uses the North American Datum of 1983, or NAD83 as it'll show up in ArcMap. Each state uses one of two map projections. States with a predominantly north-south extent use the transverse Mercator projection, and states with a predominantly east-west extent use the Lambert conformal conic projection. However, even the use of projections is not always consistent with the directional orientation of the state. For example, due to the east-west orientation of the state plane coordinate zones that subdivide the state, California uses the Lambert conformal conic projection, even though the state itself has a north and south extent. And remember, I'm talking about the Lambert conformal conic and the transverse Mercator because those are geographic coordinate systems and datums, which this state plane coordinate system, which is a projected coordinate system, is based off of. Again, like the UTM system, eastings and northings in the state plane system 1983 ensure that all coordinates are positive numbers. However, there are some significant differences. Measurements used for eastings and northings in the state plane coordinate system are inconsistent across the nation. Initially, the state plane coordinate system measured eastings and northings in feet. The state plane coordinate system 1983 converted to the metric system during its creation. However, most maps published by the U.S. federal and state governments still use feet, even if it's in that state plane coordinate system 83. Each zone in the U.S. also has a unique shape with boundaries following state and county lines. Nearly every state divides into a variable number of zones. Unlike UTM zones, which follow lines of longitude, state plane zones typically follow county boundaries for administrative simplicity. Most states have anywhere between 2 to 6 zones and use cardinal directions to designate zone names. Names such as north, south, east, west, or central identify the zones. States with more than 3 zones tend to use numbers instead. For example, California uses a series of Roman numerals from I or 1 to VI or 6. Zones within the state plane system 83 also have a unique set of standardized codes called the Federal Information Processing Standard, or FIPS codes, and you'll see this when you start to become more familiar with attribute tables, which will be associated with geographic data. These codes are used as an alternative to zone names or numbers to help computer systems manage large data sets. Another inconsistency of measurements is the way the state plane coordinate system defines false eastings and northings. The false easting assigned to the center of each zone varies by state based on the map projection. Zones using the Lambert conformal conic projection have a central meridian with a larger false easting than zones using the transverse Mercator projection because they are bigger east to west. Specific values vary by state. Every zone in the state plane coordinate system 83 has a different northing value with an origin somewhere south of the zone coinciding with a parallel of latitude. Okay, so that wraps up this lecture. We'll just go over some of the main points really quick. So we must project our data in order to derive meaningful spatial measurements in a GIS. We can't derive accurate measurements of distance and area if it isn't projected. Degrees or units of measurement on a globe are not uniform. So points are projected from the round Earth surface onto a flat map surface. And map projection process always introduces some kind of distortion, which can include area, shape, angles, distance, etc.